So, hello everyone, we will continue with the thermal comfort. This in this segment we are now discussing the basic factors which controls the thermal comfort sensation, and the basic there are 6 factors we have mentioned, and we have discussed the air temperature, radiant temperature, air velocity, and now we are discussing the environmental, one of the environmental related factors, which is humidity related factors. So, which is extremely important, the factor that typically, and this humidity related factor we cannot consider in isolation. It has to be in combination with other factors like air temperature or radiant temperature. Typically humidity between 40 to 70% relative humidity does not have much impact on thermal comfort, and if it is more than that, it is in and 70% and particularly in warm condition. So, hot and humid condition, then main problem would be that our body will not be able to evaporate whatever sweat it generates. So, it will not be able to evaporate. So, then the evaporative cooling will not be there. So, high humidity environment have a lot of vapor in the air, which prevents the evaporation of sweat from the skin. So, at high and hot humidity, so it is extremely uncomfortable, but if there is air flow at that humidity, so we may feel comfortable. So, it is related to the air flow also. The evaporation of sweat is the main method of heat loss of human in hot environment, as we have seen. So, that is that evaporation is actually assisted by the air flow, and in any personal protective clothing like firefighter clothing, if the wearer is not able to the release of that evaporation of the sweat, if it is the its vapor permeability is poor, so in that case he will not be able to be comfortable. Okay. Now, the next factor is the clothing related factor, the clothing insulation, which is very important for to keep body thermally comfort. So, by clothing by its very nature interferes with our ability to lose heat to the environment. So, if we want to restrict the heat loss, we can increase the insulation of the clothing. So, thermal comfort is very much dependent on the insulation characteristics of clothing. Wearing too much clothing is sometimes creates problem, because it will give unnecessary the insulation, which may cause the heat stress. So, it is a primary cause of heat stress in that personal protective equipment. So, if the clothing does not provide enough insulation, so on the other hand, if it does not provide enough insulation, so that means it will our body will lose heat unnecessary at higher rate. So, we may land up with either frostbite or hypothermia, okay, in extreme cold condition. So, clothing insulation and control of this clothing insulation is very important. So, that we will discuss with the different studies how to control this clothing insulation. So, clothing is both potential cause of thermal discomfort, as well as it controls the it actually it enhance the comfort as it adapt to the climate in which we live in, or we play. So, we may add layers of clothing. So, depending on the type of environment, so we can adapt gradually. If we need to restrict our body heat to go out at higher rate, we may keep on adding the layer, and if we feel it is giving higher insulation, we may remove. So, that way by changing the type of clothing we can control the our heat balance. So, it is important to identify how the clothing may contribute to thermal comfort or discomfort. So, for a particular condition, so for a particular air temperature in front of radiant heat temperature or in a particular air humidity or air velocity. So, we have to select depending on our physiological condition, we have to select the particular clothing to keep ourselves comfortable. It may be insulating or higher insulation or lower insulation. So, accordingly we have to select our clothing. So, it is very important. And last one is that metabolic heat. So, different it depends on the it varies from person to person. So, depending and different level of activities. So, at different level of activities and for different person. So, if we know the level of metabolic heat, then we can select our clothing. So, the more physical work we do, so higher will be the metabolic heat will produce, and more heat we produce, higher rate of heat loss we should actually we have to have, otherwise our body will get overheated. So, and the impact of metabolic rate on thermal comfort, it is very critical. Person's physical characteristic should always be kept into mind. So, there are various factors like it's his weight, age, fitness, okay, height. So, all these things actually related with the it controls the type of metabolic heat. So, and the thermal behavior of human body and transmission characteristics of is shown by this diagram. So, heat actually heat flows in and out by conduction, convection and radiation or by sweat evaporation. So, basically it is mainly the heat is in a dry heat, it is released through clothing by conduction, convection or radiation. This is the dry heat, okay. And in case of say heat also we release in terms of the moisture in liquid or in vapor form. So, in the form of latent heat at various phase it actually we release heat transferred by this process of condensation or evaporation or by freezing or melting. So, the latent heat at different form it gets transferred. So, moisture transmission through clothing we will discuss in the next segment in detail by water vapor diffusion, okay, convection in void space within the textile structure, moisture diffusion in fiber surface, liquid water diffusion through capillary, which we normally know it is known as the wicking characteristics, capillary channel, moisture condensation. Sometime moisture gets condensed if the path is longer and it is at extreme cold condition, it gets condensed or evaporates and freezing or melting may take place. So, these are the moisture related phenomena, and clothing assembly and this entrapped still air influence the heat and mass transmission of the human. So, in heat transmission actually majorly depend on the how the clothing entrap the still air. So, that we will see that by controlling the amount of entrapped heat we may control the heat and mass transmission. So, if we can entrap more and more air inside the clothing ensemble, so we can increase the insulation without increasing the mass, without increasing the amount of quantity of material. Also we can control the moisture transmission. So, if we see the generation of body heat, that is biological and physical activities in terms of metabolic heat. So, its thermal comfort is achieved by release of heat, by sweating, by various other physiological activities. So, we can achieve the thermal comfort, and it's basically through, we have to do all these things through clothing, and by the means of the heat transmission through clothing. One is the dry heat transmission through the clothing by conduction, convection and radiation. Another way is that through moisture transmission, that is water vapor diffusion, liquid moisture diffusion through fiber, or various through various mechanisms. This part we will discuss when we will discuss the moisture related comfort aspects. Now, we are going to discuss in detail the dry heat transmission. So, as we have mentioned that with the increase in activity, human activity, our the metabolic heat generation increases. So, as we increase the activity, so it generates more and more heat. So, you can see that at when we sit we sleep, it generates around 35 to 45 watt per square meter. That is the type of heat we generate, but when we play an high active game, so we may generate approximately 10 times of that heat we generate. Now, let us try to see our human body how. So, if we see our human body, it, as we have discussed that it receives heat, it does not reflect back. So, human body absorbs all the electromagnetic radiation. So, that is which is the nature of the black body. So, human body we can consider as equivalent to black body. So, no EMR, electromagnetic radiation pass through or reflect. Okay. So, the object appears black when it is cold, that is why it is called black body. But in as the temperature increases, so but at particular temperature, if the black body is surrounded by other objects in thermal equilibrium condition, then it emits exactly as much as it absorbs. Okay, it is called black body radiation. So, it will start radiating the heat, okay, if it is surrounded by the different objects. Okay. The wavelength of the emitted light is directly proportional to the temperature of the object. So, that is at room temperature it emits only the infrared light, okay, which is not visible, but as the temperature increases it starts emitting the visible light. So, for any, if we increase the temperature, so it will start emitting the visible light. So, that the human body can be considered as black body. The human energy is radiated in the form of electromagnetic radiation. So, we whatever heat we generate, we actually release the heat in the form of electromagnetic radiation. So, the net power radiation is, it is a whatever the power we radiate, whatever heat we radiate, it is basically it is a difference between the power emitted and power absorbed. So, we keep on absorbing the heat and we also release the heat. So, net emission is net emitted heat is that is the difference between that and the total heat. Now, try to see the simple calculation. The total heat energy radiated by an adult male in one day is about 200 kilocalorie. Okay. So, that the whatever food calorie we store, the total throughout the day we emit 2000 calorie, 2000 kilocalorie, okay, heat we emit. So, that much heat we emit. Now, let us see the calculation. As we have seen that primary metabolic rate, say when we sleep, typical value is at 40-year-old male, healthy male is about 35 kilocalorie per square meter per hour. That is the rate which we produce, okay, which is equivalent to 1700 kilocalorie per day. So, if we how do we get this 1700? Because 35 kilocalorie per square meter per hour, if we assume our body surface area 2 square meter. So, 35 multiplied by 24 hour in a day multiplied by 2. So, we get around 1700 kilocalorie per day. So, a person actually release that heat 1700 kilocalorie, it generates that much heat. Okay. So, this is the heat he generates when he is sleeping, 1700 kilocalorie heat. Now, if we see when he is little bit active, we normally do not sleep 24 hours, if we active. So, average activity, if we see, it is typically it is a 70% more than this 35. So, its average activity, it is 50 to 70% more than that when he is sleeping. So, that means it is a 50 to 70% greater than the basal rate. So, ultimately what are we getting? So, it's if we see 70%. So, 1700 he is generating for 24 hours multiplied by 1.7. So, multiplied by 1.7. Okay. So, the thermal loss, that is mechanism of the body, it is a conduction which is very low. We have already seen earlier, through conduction it is a low, because most of the textile materials are insulating in nature. Even air is insulating. Convection is very high when it is very significant when it is air is blowing, it is a forced convection. Radiation is very high. Sometime if in case of forced convection, when air velocity is very high, so it may actually suppress the radiation also. Otherwise, radiation is generally very high, and then evaporation. So, in case of if the dry air condition, so humidity is low, so evaporation will be high. So, we are discussing the radiative heat. So, radiative heat loss, the heat loss by radiation is approximately 2/3 of the total heat loss by other total method, total mechanism. So, conduction, convection, radiation and evaporation, among all this, if we take all this together, 2/3 of this is by the radiation, as radiation is normally high. So, that means if we see 1700 is the heat he is generating throughout the day when he is sleeping, multiplied by 1.7, because he is not sleeping, he is active. So, 70% higher than that, 1.7, and multiplied by 2/3. So, it is coming out to be 2000. So, 2000, that this value we have discussed earlier. So, 2000 kilocalorie he is generating heat. Okay, a person is actually it is radiating, the radiative heat is typically 2000. Okay. So, ambient air motion causing forced convection, okay, as we have discussed, sometime actually reduces the relative importance of the radiative heat loss. So, in that case, if it is air is moving, then this factor 1.7 will not be there, it may be 1.5 or maybe 1.4. So, in that way, so the radiative heat loss will be lower than the other heat loss. So, in that total heat loss will remain same, but this factor 2/3 and 1.7 may get changed, but in normal condition. So, it is typically 2000 kilocalorie. So, another thing is that our as we have discussed, it is not steady state condition. Our body cannot be it is normally it is not in steady state condition, and heat flow condition is always in dynamic. So, basically throughout the year season changes. So, our temperature gets changed in summer, winter, even its humidity condition changes. And in addition to this, the atmospheric condition like temperature, vapor pressure, air velocity is always change. So, it is but if we feel that okay, a particular cloth will keep ourselves comfortable throughout the day, throughout the year, it is not possible. So, due to all these variables. So, internal body condition also changes. So, our metabolic rate, our activity level also changes. So, accordingly if we want to keep ourselves comfortable, thermally comfortable, we have to actually use different types of clothing. So, our total thermal behavior always changes depending on the quantity of food consumption also, okay, nature of activities. So, these are the factors which come. So, discomfort arises when there is an imbalance. So, these are the conditions, the summer, winter, our activity level, our type of air velocity, type of vapor pressure. So, all this activity, all these factors actually controls the thermal comfort nature, but we feel discomfort when there is an imbalance between the atmosphere and internal condition. There has to be proper balancing of heat balancing, otherwise we will feel uncomfortable. So, the clothing requirement should be balanced with the external atmospheric condition and internal heat production. So, that these things always changes. So, our external environmental condition always changes, our body physiological condition, body heat production is always changes, but our clothing has to be such that it keeps the balance, okay, so that we feel comfortable. So, that means our body core temperature should be around 37 degrees Celsius irrespective of anything, any climatic condition, okay, and any physiological activities. Okay. So, under steady state condition, although we hardly reach any steady state condition, the energy produced by the body should be equal to the rate of heat transferred from the body. So, we know that it is a typically it is a 5 mechanisms: conduction, convection, radiation, evaporation and respiration. So, if we assume that the heat exchange from the unit surface area of body to the environment, then the general heat balance equation is this. This is the general heat balance equation per unit area of the body. So, this takes care of all these principles of all these mechanisms of heat transfer. So, what are these? So, M is the metabolic rate which actually our body produce, and W is the external work which is lost. The metabolic heat is lost by some external physical work also. So, that M minus W, which is the net heat inside our body, which has to come out from the body by the its heat loss by convection, by heat loss by conduction, which is normally it is very low. Convection convective heat loss is, it depends on the air velocity. Heat loss due to respiration, sensible respiration, it is there, which may not be directly related to the clothing. Heat loss by radiation, maybe through clothing or maybe open area. E rays is the evaporative heat loss due to respiration, and heat loss by evaporation from the skin. So, this is from the skin, evaporative heat loss by respiration. These are not directly related to the this clothing, okay. And the heat loss by conduction is that the rate of heat loss by conduction is influenced by the nature of clothing. So, this is the conduction which we can control if we can control the clothing type of clothing. So, let us discuss one by one. This equation for heat loss due to convection is C is the heat loss due to convection that we have seen earlier. It is a convection which is equal to it is a watt per square meter. Here all these are converted into watt per square meter, which is it is a product of clothing factor, area factor FCL is the clothing area factor, coefficient of convective heat transfer HC, okay, and TCL clothing surface area, temperature of clothing surface, and TA is the ambient air temperature. So, as from this equation we know that as if we increase the clothing area factor and if the convective heat transfer is high and if the temperature difference is high, then we will have higher convective heat transmission. So, what is clothing area factor? It is a basically it is a ratio. Clothing area factor is a ratio, the area which is actually covered by our cloth by the total area of a total area of the body. So, it is a ACL is the it is area by clothed body, okay, and AD it is a total area of nude body, total area. Similarly, for mannequin also, for mannequin test it is ACL by A is the total area of the mannequin. So, that is so that means higher is the value or this FCL is that clothing area factor. So, the convective heat transfer coefficient H, it depends on the air velocity, okay. So, it is basically directly related to the air velocity. If we increase the velocity of air, so convective heat transfer coefficient will change. So, it is basically it is a function of air velocity, and also it depends upon the position of the person and orientation to the air velocity. So, if the orientation towards the air flow it changes, the that HC value, that is convective heat transfer coefficient value changes. So, if the air velocity is air flow is some in a particular direction, okay, if the person's position changes, so that HC value will get changed. So, HC is depending on the mainly on the air velocity and also to some extent on the position and relative position of the person. So, there are studies carried out. So, HC value has been plotted against the velocity of air. So, it is this is an empirical equation. So, which has been this is the 12.1 multiplied by velocity to the power 0.5. So, this is the empirical equation from where we can get some idea about the value of this HC. This is the coefficient, and clothing area factor FCL we have that clothing it can be evaluated by following empirical equation. So, that we know the clothing area factor is the ratio, but there is another empirical formula which is related with the flow of the that is insulation of the clothing. So, this is the clothing area factor FCL. It is although it is unitless, but it is actually empirically this is we can get this value, okay. If we know the flow of the it is directly related with the flow of the clothing, because it is higher area covered will means higher clothing area factor, that will indirectly give the value of the flow, okay. Now, radiative heat loss, as we know that it depends on the mean temperature of the surrounding environment and temperature of the clothing surface and characteristics of clothing and environment. So, this is the basically it is basically the temperature difference. So, this radiative heat loss, and the equation for radiative heat loss as we have also seen earlier. So, it is basically this is the equation, radiative heat loss R is actually it is a function of the fourth order of the temperature. So, if we see where this sigma is the Stefan-Boltzmann constant, okay. And what is Stefan-Boltzmann law? It is basically total energy that radiates per unit surface area of a black body in unit time is proportional to the fourth power of the thermodynamic temperature. This is the it is actually it changes with the fourth power of the thermodynamic, and epsilon Cl is the emissivity of the clothing. So, if we can control the emissivity of the clothing, we can control the R value, okay. And Tf is the Tr is the radiant temperature, okay. That is, if the radiant temperature here it is a less than it is that is the temperature of the surrounding environment, it is here in this case if it is less than the body the clothing surface temperature, that means we will release the heat, and Vf means it is a view factor between body and surrounding, okay. It is about 75%, it is a view factor, that is effective area of the body for radiation. So, that is the view factor, and heat loss mechanism which are not directly related with the clothing is that this is the rest of other mechanism, that is heat loss due to respiration, we will not consider here, evaporative heat loss due to respiration, latent heat, and removal of heat from the body by due to the evaporation of perspiration from the skin. That is which is actually this skin means which is not covered by the clothing. If it is covered, that means our clothing will come into picture. Okay. Now, we will discuss the Newton's law of cooling and how this law helps us to derive the equation for thermal resistance or thermal transmittance. So, what is Newton law of cooling? It states that the rate of change of the temperature of an object is proportional to the difference between its own temperature and ambient temperature. So, if the difference that is high, that is the heat flux, the temperature difference is high, that means the rate of change of temperature will be high. So, it is proportional. So, rate of change of temperature is a dT, d capital T the temperature by dt the time. So, is proportional to the difference between the temperature between the material and the ambient temperature T A. Okay. So, dt by dt is proportional to the T of the material and T of the ambient temperature. Okay. And where T T is the temperature of any material at time t, and T 0 we will see it is the initial temperature, because a temperature keeps on changing. Okay. The temperature rate of change of temperature, T A is the ambient temperature. Okay. So, at any time at initially it was T 0. So, at certain after certain time its rate of change of due to temperature change it has become T T. So, this rate is proportional to the temperature difference. So, initially if it is say it is say at lower temperature. So, it is so that time the temperature difference was high. So, the rate of change of temperature was high. So, clearly if the material is warmer than the ambient temperature. So, T T minus T A is more than 0, then the material cools down. So, it is a typical, it is a if it is warmer than environment, material will cools down, which means that the derivative dt dt should be negative. So, that means that is why this negative sign is given here, okay, and k is the positive constant, which is known as the cooling constant. So, this the proportionality, and then it is a k is a constant. So, dt dt equal to minus k T T minus T A. This is the general formula where k is the cooling constant. Now, the difference between material and ambient temperature at time t, y is a function of t, is equal to T T minus T A, and at initial stage y 0, T 0 minus T A when at the time t equal to 0. Now, the derivative of y t, if we try to get the derivative using Newton's law of cooling, so what are we getting? dy dt equal to d dt by T T minus T A. So, ultimately we get the dy dt equal to minus k y. So, now this actually solving this differential equation, finally we get this is the value. So, if we solve this differential equation, y t equal to y e to the power minus k t, this is the solution of this differential equation, where and we if we replace y t by T t minus T A and y 0 by T 0 minus T A. So, we get this form, and by rearranging this we will get T t equal to T A plus T 0 minus. So, this is the generalized form of from the Newton's law of cooling. So, by rearranging again we get this value. So, T 0 by T ambient. So, T A we have used earlier. So, T O T 0 minus T ambient equal to E to the power 1 by R C multiplied T. So, here if you see k is the cooling constant has been replaced by 1 by R C, where T is the temperature of the body at a particular moment, T 0 is the initial temperature of the body, T ambient temperature, T is the cooling time. This T is the cooling time, and this R is the thermal resistance. Here this C is the thermal capacity of the system. So, K has been actually replaced by 1 by R C. So, where C is the thermal capacity of the system in joule per Kelvin, R 1 is the thermal resistance of both the fabric medium and the air medium around that. This R is the both this medium. Now, if we try to segregate, and that R becomes R 0 plus R, where R 0 is the thermal resistance of air and R is the thermal resistance of clothing layer. So, and again by rearranging this. So, this is the, if we know the cooling constant from Newton's law, then we can calculate the resistance of the clothing. So, resistance of the clothing we can, by rearranging that equation we get in this form. So, where K 0 is the cooling constant of the system without any fabric, K is the cooling constant with fabric, and C is the thermal capacity. From there, now this is one way of expressing the thermal resistance of the clothing. Now, if we see if we know the thermal resistance if we can calculate from there. So, as well as knowing the thermal resistance as well as the fabric sample surface area, if we know the surface area and the thickness d, surface area is, then we can calculate the thermal conductivity. So, thermal conductivity lambda is, the unit will be watt per meter Kelvin, can be calculated by 1 by R multiplied by d by S. So, where R is the thermal resistance. Another way of looking at that is we can measure the heat transfer coefficient H. So, earlier we measured the thermal conductivity. So, this is the thermal conductivity lambda, the unit is watt per meter Kelvin, okay. And here the heat transfer coefficient is the unit is the H, it is expressed in H, which unit is watt per square meter Kelvin. So, that heat transfer coefficient is another way of expressing the thermal conductivity of the clothing, where dq dt is the it is a measure of heat transfer rate. That means, it is a unit is in watt, S is the area of the fabric. So, watt per square meter, and the temperature is difference of temperature, the average temperature of the system and the ambient temperature, that is the in Kelvin. So, watt per square meter per Kelvin, that is the unit of heat transfer coefficient, whereas thermal conductivity the unit is watt per meter per Kelvin. So, that two ways of expressing the thermal conductivity, and this is the way of another way of expression. The Newton's law of cooling is applied to evaluate the thermal properties of the textile material. So, this is the way we can express. Now, after knowing all these things, so if we know that the amount of heat and thermal capacity, so that we can calculate the temperature of the body. Okay. So, dq dt into R is the thermal resistance of the body. So, this R we can calculate. Now, after all these things are steady state heat transmission, then next is the transient heat transmission of through clothing. So, what is transient heat transmission? The human body, it is normally it is in temperature of human body is it is 30 degree Celsius, 37 degree Celsius sorry, and the skin temperature we know it is around say 34 degree mean skin temperature, and clothing if we see clothing temperature is normally it is less than the skin temperature. If it is there, then heat will flow from the skin to the clothing and we will feel coolness. So, this phenomena is called transient heat flow, and the detailed transient heat flow behavior we will discuss in the next class. Till then, thank you.